Hello everyone, welcome to Natural Language Processing. And in this session, we are going to discuss about word-to-vec implementation. So in our previous session, we have discussed about how or what's the theory behind you can convert a word into a vector, which doesn't even not only telling only the frequency of its occurrence. Instead, it is going to tell you its meaning. Maybe like for example, we have seen if you have a word known as king, which refers to a monarchy, so a leader, and we have another word known as queen, and there is some difference and relation with this. And if you have another word which is something like a food, maybe pizza or burger, so these words are similar, and words like king, queen, like battle, these are similar. And like if you consider the words like king and a food, there is no such relation with that too, right? Maybe if you consider a word like has tail, for a king, they don't have a relation. But if you look at a horse, a word known as horse, it has some relation with this having tail, because horses have tail, right? So this meaning, if you want to transfer, you can use word-to-vec. And we have seen there are two types of implementation which has been used for training. So one is called as continuous bag of words, another one is skip grams. In the previous session, we have discussed about these introduction and the theory behind it. So with this level of knowledge, we are going into hands-on. So word-to-vec can be converted with many different ways. You can even build your own word-to-vec converter with the help of deep learning neural network. So we'll be covering both of all the possibilities which we have. You can train your own or you can download from pre-trained. So we'll be utilizing that. So before continuation, we will also once again go through what is word-to-vec. So word-to-vec is a natural language processing approach that includes learning vectors, representation of words known as word embeddings, and these word embeddings can record semantic links between words, making natural language processing more effective. And for example, the vectors for the words like king and queen can be similar because they both related to royalty, and this method has been utilized in wide range of applications including language translation and text categorization as well. And if you want to imply this, you can train your own word-to-vec model using libraries like GenSim or TensorFlow. Okay, so if you want, you can use TensorFlow. With the deep learning knowledge, you can create your own neural network and train it on your data. Or there is something known as GenSim from Google. It's a Python library. So they provide API and they provide the model as well. You can get their model and you can train on that model with your data. So that is also a training which you can do, which we will do for our data. Or you can also use the API to download the pre-trained model. It will be like taking many days for training because it is trained on huge amount of data. But if you want to use, you can just download it in minutes, and you can utilize that representation as well for your conversion. So that is word-to-vec, and let us go into the implementation part. So starting with from scratch using deep learning. So let us build our word-to-vec from scratch using deep learning. So let me go into our Google Colab, and what we are going to do is we'll be utilizing this particular cell, our data, as a sample for working with it. So we'll be training a model on this particular set of data, and before continuation, later, after we see this example, we will be using the word-to-vec API, which is from Google, from GenSim. So this is, we are going to download it. First, let me start running it. And the reason is, it is going to download nearly a GB of 1.5 GB of file. So let it download. In the meantime, we'll come back because we need this file to be there. So this is a API. If you don't want to train your model from scratch, you can download pre-trained weights. So let it download and we'll use it later on. And now what we are going to do is we are going to train data on our own deep learning neural network. So if you look at the data, so you have bunch of sentences here which has new line characters and all, which we don't want it to be present. So what we are going to do is, first for I in range, let us do some basic pre-processing on the length of data. So for all the length we have, it is going to just first convert it into dot lowercase. So we are turning them into lowercase, and then we can also replace. So we are doing the basic pre-processing here, any new line character into nothing. And once it is done, let us print our data. Okay, so this is already a string object, and we need it to be of sentence. So what we can do is we can replace, we can perform sentence tokenization. We can just call data.split, and wherever you have full stop, just split it. You will be getting sentences. So if you look at the data now, you have a list of your sentences which new line character. So I'm going to transform them into lowercase, and then we'll replace them as well. So now you have the processed one. Okay, so you have your text available for you, and what we can do is we are going to remove some of these stop words, and let us manually type our stop words here. Don't go for the predefined stop words. We have some simple sentence. Let us select the is a stop word, then is a stop word, will be. So these are some of the stop words which I can see in the sentence as well, right? Yeah, only. So we have only the important things to be present there. So we are doing this. Comma, then we can go for there. So let us see what else we have. So we can look into the text for now. Okay, so we won't be doing every time. Since we are building our own, let us do it from scratch. Something like now and at and it. These are some of the stop words which I don't want my sentence to be present. Usually we can go with the library itself from NLTK. Fine. So the filtered data, let us create a list for filtered data, and for sentence in data, let us go with the temporary list, and for word in sent.split. So you are splitting the sentences, and what we are going to do is each word we are going to check if it is okay. If not in, right, so not in stop words, then we can call the temporary to append those words. So once this is done, you will be getting a sentence after this loop ends. So after that process inner loop ends, we need to store it in the sentence. So it will take sentence by sentence, split them into words, and check this process and give us back. So we'll add this, and then finally let us print our filtered data as well, which is removed of stop words. Yeah, so this is what the result looks like. So we have done some pre-processing here, something like the future king prince. So this is what the transformed sentence looks like. Fine. So now we are going to create some bigrams. So let us create some bigrams. So for words list in filtered data, let us do it manually. So for I in range, so we know what is a bigram. So you two word combinations. So if you know the length of the word, and for the last word there is no bigram, right? So you need to stop one step before. So I'll run a range of one step before, and from here I'll create another loop for j in range. For the next word, it should be the next word, which is I plus 1, and it should run till the words list. So you can get the last word as well. So with these two, we can just call bigrams dot append. So first let us perform appending words underscore list of I, comma words underscore list of j, and then the vice versa as well. So we can just do bigrams dot append words underscore list of j, comma words underscore list of I. So once this both is done, let us see the print grams by printing it bigrams. So printing the bigrams will give us, this is what the bigrams is: future king, king future, future prince, prince future. So we have created a bunch of bigrams which all the combinations as well. So let us also do the unique words for checking the vocabulary. What we can do is I'll create a list of all words, and for by in bigrams, let us ask to extend or add it in the end. We can add bi, and once it is done, I'll just go with all words is equal to a list of a set of all words. And why we are doing particularly this is a set will have only unique values. So when you pass it through a set, it is going to remove all the duplicates, and let us also print total number of, okay, I hope this is PO, right? Unique words. So you can check the unique words with the help of just if you just pass length of your all words, you will get that. And this is going to give us the vocabulary and the result. So this is what all our vocabulary is, all the unique words in our particular data set. And this is what the total count is, which is 12. And I hope it's clear, and we can go into creating a dictionary of words. And for that, I'll create a words dictionary. And whatever we do, this is, you can implement from scratch like this, but we usually go with our NLTK, right? So I prefer, since we are building our neural network also from scratch, let us do the backend processes in the scratch itself. Why not? And for word and all words, what we are going to do is we are going to just call, it's already unique word. So words of dictionary for word is equal to the counter. So we can also add counter plus equal to 1. So it is going to just assign them one number based on its location. So if you just look at this, you will also get something like 0, 1, 2, 3 for each of your word you have their position. So now we are going to perform one hot encoding, and let us do it manually. Like the bag of words, it is going to tell the representation when you perform continuous bag of words, which is CBOW, which is word to vec. So we'll import numpy as np, and what we are going to do is we'll perform one hot data is equal to np.zeros, and we need to get zeros first. So first we are creating zeros of 2D with the length of like the same. Okay, so now we will be getting a 2D, which is something like this. And why we are doing it, we are going to create our vocabulary. So we are getting all the words and their representation. It's all 0. It is not present everywhere. So we are going to update its presence one by one. And how we are going to do is for I in range. Let us go with length of all words. And then we can go and allocate one hot data of I of I. So is equal to 1. So 0 of 0 will be 1, 1 of 1 will be 1, 2 of 2 will be 2, which tells the presence of that data. That's what the one hot we are trying to do here. So we'll update this, and once this is done, we can go and update the next step as well, which is one hot dictionary is equal to empty dictionary, and then we'll set a counter is equal to 0 as well. And then for word in all words, so we add the unique words, right? So we are going to pick that, and what we are going to do is we call one hot underscore dictionary of word for each. I'm going to create the one hot underscore data of the counter. We'll be getting that. So from that particular location, it is going to get that. For 0 or 1, you will get the respective array, which is something like for that particular word, what is the array? For the next word, what's the array? Because counter is going to take 0 and then first and second the next array as well. So once this is done, I also need to increase the counter, otherwise it will be staying in 1. So once it is done, let us also do something like for word and one hot data. Let us see it. What is that? One hot data. Let us go with print word comma its representation, which is one hot underscore dict of that particular word. So let us do this process and see what do we have here. Okay, we are getting some error. Let us sort it down. So earlier we have done some things like this. One hot encoder. We are particularly getting the error in this last particular line. Yeah, and the problem is here we have to pass one hot dict, not the data. So if you run it, you will be getting the one hot representation for each of your word in a dictionary. For boy, this is the representation. For daughter, for women, so you get their representation one hot encoded manually. Okay, so now we are going to do it for, we'll do some process for our bigrams as well. So I'll create a list of X and create a list of Y. So for bigrams, and why we are doing this is, let us see first for by in bigrams. What we are going to do is we'll call x dot append in the end, and we are going to add one hot dict of by of 0. So you are going to get that particular from bigrams, you are going to get the word, and what's the 0th word you have there, you are going to get that dictionary. Maybe if you have in bigrams, maybe you have boy and daughter, so you are taking only the boy and you are getting the particular array and you are appending it in X. Okay, so like that we'll do for other as well. And in Y we need to append the next half, which is the target, which is going to be one hot dict of by of 1. So we are going with this window size of 2, and once you complete, if you look at the value of X, okay, let us turn it into array. X equal to np dot array of X and Y equal to np dot array of Y. Yeah, so looking at X, so this is what we have the representation for the pigrams, and Y will be our target word, which is to be predicted or the relation. That's how we do, right? We create a window size, we create from our data itself, we pick a window size and we pick the middle word and make it as a target. That's what we do in continuous bag of words. So we'll be training that in that manner. So that's what we are going to do here as well. So we have prepared our data. So now what we are going to do is we are going to imply it manually. So from TensorFlow dot keras dot layers, let us import dense, and from TensorFlow dot keras, let us import sequential, and let us go with import TensorFlow as TF, and let me go with TF dot a random seed. So I'm going to set a random seed so that every time you rerun it, you may get same random numbers when you kickstart it. And the reason why we are doing this is because like we are just training for our sample, and every time you rerun, they are going to start with some random weightage, and it is going to cause us trouble, because once again we are limited in our data and we are just training it on a limited set of data. We may need to get the reproducibility in this. So I create a model with sequential, so a way we used to do. So we are just going to build a 2-layer neural network. You can add or you can create a list like this with dense is our embed size, comma, and the activation function I'm going to apply here is linear at the beginning, and we know linear will do nothing, so you are not applying any ReLU or leaky ReLU or something like that. And the output I need is the amount I have in the Y, I want to match that, and the activation here is softmax, because softmax is going to help me to find who is the most probable word. And once it is done, you can also compile this with model.compile. I'll go with the optimizer of Adam, and we are going to go with the loss value. Since it's a multi-class, we go with categorical cross entropy. So everything is ready. We can go and call our model to fit on X, comma, Y, and I'll run it for epoches of 3000, and let us do like patch size of let us go with 256, and then you guys see, right, whenever you train a neural network, you will be getting the symbols which tells that the running how many epochs has been completed and all. If you don't want it, you can go and change the verbose. Maybe if you switch it off to set it to false, it is going to not occur, so you can just see the output, not to see the process. So let it train, and in the meantime we are going to visualize the result as well. So let us go and do, for example, the weights for each. So the weights is equal to model.get underscore weights of 0. So you can get the weights particularly. So let us visualize the weights. So you get, for all the features you have, you get the weightage. And now we'll extract for each word. So word underscore embeddings. We need to get our word embeddings. After training, we can go for word in all words, all the unique words we had, right? So we can call word underscore embeddings, create a key which is the word, and the result is going to be the weights of the word dictionary, words dictionary, I hope so. and I will pass the word inside. So was our word dictionary. Yeah, so we had our word dictionary here, right? So we will be taking from there and we'll be pass the word. So get the array and then we'll map it. So once this is done, let us run it. Once this is done, you can go and print your word embeddings, which is going to give you the embeddings which has been done, and it will be in the shape of something like this. Tells the representation of it. Okay, it's the word boy, the word daughter. So it tells that how probable the next nearer words are going to be, and this is the representation of it, which is the numerical representation or the encoded detail for the particular word. And what we can also do is we can visualize this. So let us go and use matplotlib.pyplot as plt, and let us go with for word and a list of words dictionary.keys. We will get that, and all the unique words we are getting, and we are going with the coordinates. So you can get from the word embeddings. So that x and y you are getting, right? It's a representation in x and y axis. The two values for boy and the next word and all. So let us go with dot get. Actually get, it's a dictionary, right? So I'll pass the word inside. Maybe if you look for boy, it is going to get the x and y axis, and we can just need to plot a scatter plot where the x axis is going to be the coordinates of 0 and the y axis is going to be the coordinates of 1. And we can also do some annotation, which is to tell that what it is. So the word, and then we pass the coordinate of 0, coordinate of 1. So if you run this, yeah, so this is what the representation of 2D which we have done after training. Okay, so see here, the words like queen, beautiful, and daughter, woman, princess are towards the side. You can see they are related. And other words like man, prince, king, son, boy, strong, so these are towards another side, right? So this, if you train furthermore on huge amount of data, you can represent each word in a vector representation like this, and this is what exactly the word to vector we were talking about, and we have built it hands on. And this is a way of doing it, and we have done it successfully. We have built one hot encoder, the continuous bag of words from scratch within our limited data, and we have trained this in this particular way. This is how, if you have huge amount of data picked or collected from entire corpus of internet, from dictionary, from libraries, from various sources, you can train. And one such thing which is trained already is something like our Jensen. To see what the word to vec which is available already can do, let's download a pre-trained model and play with it. We can fetch from Google News dataset. It has nearly 3 million words and phrases. We just had 12 unique words. This has nearly 3 million words and phrases. So if you want to train, it will take hours or even days to do, but it's already available. So we can download by calling the API, and API is used for, you can download different data set, and I am interested in only this particular Google News 300. So there are some other keywords which is trained on different set of data. You can pass it and download it and use it. So one such thing which we have loaded here, which is in WV, I have the Gensim loaded. So let us look into WV. Maybe if you have a new word, for example, I want to have the word vector for the word king. So you will be getting a vector. Okay. So we got, for example, if you pass it here, what we have, if you made the prediction and get the embedding for it, you will be getting for just 2. But here it is mapped to these many, how it is related with other words in the vocabulary. So you can check the length of it as well. Let us check the length of it. It is 300 because this is trained with a limit of 300. And if you look at king, okay, let us try to get the word of king. And you can subtract this. For example, if you want, you can subtract it with the word of queen. So you can do this process as well. You will be getting a resultant vector, and this can be done. And also you can play with this for a few more things. For example, you can call this word vector, word to vec, and just call for most underscore similar. Who are all words are most similar? Maybe if you look, check for bad, it is already trained data. It is going to give you what all the most similar word to this particular word bad. So good terrible, horrible. So these are related words, right? So you get it. And it is, once again, remember, this is trained on news data. So for some representation you may not get. For example, bad and good are really opposite, but in the contextual way it is something which tells the meaning of it, right? Awful, dreadful, they are good. Maybe if you look at king, you can understand other words which is related, like queen, monarchy, crown prince, sultan, ruler, princess, and all. Let us try for cricket. Okay, cricketing, cricketers, test cricket, 20 cricket, 20 cricket, cricketer, and again West Indies cricket. These are the most related, and their relation or the similarity is given here. It's the similarity which is high, means it's high. If you are calculating the distance, then if you have to subtract it with 1, and how much closer, it's just the vice versa, right? And you can also check for I hope word to vector similarity. For example, W1 is going to be like king, and the W2 word is going to be something like pizza. Is there any similarity? You can see the similarity is just 0.1. And if you try to do it something like, for example, kingdom, let us see the similarity, 0.5. Let us do it for queen, 0.65. So the value increases when that increase. Okay, maybe if you check for prince, 6.1. For example, if you do for great, and let us do it for good. So it gives you, this is how we transform them. If you have a particular sentence, we can pass, maybe for example, this is not good. I think we have to turn it into vector representation. Okay, so separate it, and then we can do like when we imply practically, we'll be doing the pre-processing. So you can't just pass the entire thing here. Okay, so this is a representation. So like that, we can train our data and get how it's related with that vocabulary size, which is 300, and it is general. And if you want, you can also train it in a way that, for example, we go into the final part, which is going to be like you can go for training your word to vec on your particular data. You are going to update it. Okay, so that is trained on a news data. Maybe you have some other review data, or you have tweet data which is new to this model, right? Some of the words may not be available. So in general, it can work nearly 60 to 70% good if you just get the pre-trained and just use it like we have done with the API. But if you want more, you want to adapt to your particular data, then what you can do is you can get it and you can train it. Okay, so you can get from gensim.models word to vec, and we can train it hands-on from scratch, like using this model. Okay, so that can also be done. And for that, let us go and do it hands-on, especially in our collab. So let us upload a data set, which is something like cell phone accessories. So it will take some time for uploading, and let us do it. So let us go with import pandas as PD, and the data equal to pd.read underscore csv. Let us see the data set has been uploaded. Yeah, so we can copy the path of it, and let us paste it here, and let us read the data now. And yeah, so we have to add a line known as lines equal to true. So since we are trying to read a JSON file, so if you go with lines equal to true, it is going to. Okay, the problem is we have gone with CSV, right? So we have to go with read underscore JSON with lines equal to true. So we can get, this is a JSON file, and earlier we have used this, it's a Amazon product review, but the project we have seen there is actually of different type, which is for musical data, and this is something like cell phones and accessories. We have the same format. See here guys, the review text and overall and details. Let us just go and pick our review text, which is a review text, and let us just take the first 5 guys. I'll show you guys. So we need to do some pre-processing. So in a project, I used to do all the pre-processings like removing stop words, stemming, lemmatization, all these process. You can also use this particularly, which is you can just go and apply some detail here, which is we need one guy which is known as gensim. So let us import gensim. It's a library. If you don't have, we can go and install with pip import gensim, and let us apply gensim.utils.simple preprocess. Okay, so it is going to do the basic pre-processing and give us the text ready. So I'm just applying it for the first 5 words here. It has turned into tokens, removed the punctuations, okay, done stemming or lemmatization, and it's look awesome, right? So the word processing it has just done is very simple. So we can also now do it and replace it. So I'll just do it on review underscore text is equal to, so data dot review text, and we apply the same thing here. So instead of just visualizing the first few, let us apply it on our entire corpus and let us see the result. So after this is done, we can just go with review text dot locate of 0 and see for what's the result it has done for each word, because we have a lot of text in that sentence, right? And once this is done, we can go and build our model as well. We'll see anyway. So model is equal to, you have to go and call gensim.models, where you can find capital word to capital V vec, word to vector, and you can decide, it's a continuous bag of words, so you can decide what's the window size you want. I need 10, so it will pick based on that. You have a huge amount of corpus, so we can go with that. And let us see what's the sentence of this is what the applied words looks like. This is good. So we go with window size of 10, and the minimum count will have something like 2, and the number of workers to do it as I'll keep it to 4. These are some parameters which you can adjust. So once this is done, you can go and call model to build the vocabulary. So we need to first do this by passing all your text which you have, and the progress we'll do we'll keep it to 1000. So let it do, and once it is done, you can get some parameters. Okay, so like model.epochs will give you what is the pre-trained epochs it has been setted. So it is already a parameter which is 5. You can adjust by setting a new value as well. Let us go with this. So you can just call this to train your model. Okay, so this is what we do when you have a new amount of text, new sample. We can get gensim and we can train like this by passing the text and the total examples. We have a parameter known as total examples, and we need to pass the result from model.corpus count, which we have done from building vocabulary. And the epochs I'm going to set as model.epochs, which is 5. So right, so I think this is enough, and we can just run this cell to train the model. It is just going to take a few seconds for the 5 epochs to be trained, and once it is done, now you get the result for your own data. Okay, so it is adjusted for your data, you get that particular result. And let this training complete, and once it is done, we can go with model.word to vector and call something like most similar and call for a word which is in your sentence. So it is going to give you some resultant word. I hope this is a data set which is the text review, right? Review of phone accessories from our Amazon. So if you buy a phone and accessories, how will the review will be like, either good or bad. So we'll try to implement them as well. So let this complete, and we can check what all similar to words regarding bad and all. So here when we try to do it for word, which is the API which is from Google News, similarity most similar of bad. So this is what we get from their pre-trained. So we are updating it here. Once it is done, we can see in ours as well. Yeah, let us check whether our training has been completed. Yes, it is. So this is what the corpus, the data looks like. So now let us get for the most similar for bad, and this is what we get: terrible, shabby, horrible. Okay, so this is after training. You can see, right, the difference for our data. Maybe if you look at something like, let us see whether mobile is there in our corpus. Okay, so prepaid, GSM, broadband, you get some suggestions. Let us check for the word good, decent, great, fantastic, nice. So these are some of the words from our detail, right? Maybe if you check for something like product, let us check for the word product. So this is what it looks like for the similar words which we can get, and we can turn them into vectors as well, like model dot what vector of product. So this is what the vector. So like that we can imply for our data. We can set it for new data. We can get the predictions. So once you update it, you can get for your data, and you can take this instead of your TF-ID of or bag of words. See here in TF-ID of or bag of words, we have just went with calculating its frequency and not giving importance to its semantic meaning. And here we are giving some meanings to those words and trying to convert the words into meaningful numerical representation, and we have done it successfully here. So with these things, we can jump into projects with deep learning by implementing, by giving few more pre-trained, few more powerful data converted from text into numbers. But on the other side, when you look at the neural networks, the artificial neural network can work well, but on complex data they can struggle. And for that we have to look into some architectures like RNN and LSTM, and all these are architectures which will be helpful for us to train and give few more advantage to us. So we are building towards the next step. So we can train and make our model in this way. So we'll see those contents